You may have heard that the Andromeda galaxy is racing toward us, destined to merge with the Milky Way in a few billion years to create one colossal galaxy. But here's the mind-blowing part: this cosmic collision has already begun. For the first time, astronomers have discovered that these giant galaxies have started exchanging stars, and the halo of the Andromeda galaxy is already bumping into the Milky Way's halo. Andromeda and the Milky Way are the largest galaxies in the local group, a collection of about 80 known galaxies. The local group is shaped like a dumbbell, with the Milky Way and its satellites forming one lobe, and the Andromeda galaxy and its satellites forming the other. These two collections are about 3 million light-years apart and are moving toward each other at a velocity of 123 kilometers per second, or roughly 76 miles per second. The collision between the Andromeda and Milky Way galaxies is set to be the most spectacular event in the history of our galaxy, and it has already begun. So, how did astronomers discover that the two galaxies are colliding? How do they know that stars from the Andromeda galaxy have entered the Milky Way? Finally, and most importantly, if humanity is still around, what will they see as the two galaxies merge in the future? Let's start with a common question. If the universe is expanding and galaxies are moving away from us, why is Andromeda approaching the Milky Way? The answer lies in the gravitational attraction between the two galaxies, which is stronger than the effect of the universe's expansion on such relatively short distances. While the universe is expanding, causing distant galaxies to recede from each other, this expansion is most noticeable over vast distances, spanning tens of megaparsecs and beyond. So, despite the overall expansion of the universe, Andromeda and the Milky Way are on a collision course. The concept of collisions on a cosmic scale is vastly different from what we experience on Earth. When two cars collide on Earth, it happens in an instant. The same is true for smaller objects in space, like asteroids. If two rocky objects are on a collision course, they crash into each other at a specific moment. However, when it comes to galaxies containing hundreds of billions of stars, collisions are a slow and dramatic process that unfolds over hundreds of millions of years. A fascinating example is the Antennae galaxies. Located about 70 million light-years away from Earth in the constellation Corvus, these galaxies are amid an epic collision. They are named for their long, antenna-like tails of stars, dust, and gas, resulting from powerful tidal forces at play during their interaction. Studies suggest that these galaxies have been merging for at least 100 million years, showcasing the slow yet spectacular nature of galactic collisions. Collisions play a critical role in the evolution of galaxies. The Milky Way has experienced numerous interactions and mergers throughout its history. One notable interaction is with the Sagittarius dwarf elliptical galaxy, which is currently being torn apart and absorbed by the Milky Way. This ongoing process has created streams of stars and contributed to the growth of the Milky Way's halo. However, the collision with Andromeda will be the most dramatic future event in the Milky Way's history. The first evidence that the Milky Way and Andromeda galaxies have already begun colliding comes from a special class of stars known as hypervelocity stars. These stars are like cosmic splinters, racing through space at speeds fast enough to escape the gravitational grip of their own galaxies. Imagine throwing a ball so hard that instead of coming back down, it flies off into the sky, never to return. Hypervelocity stars do something similar, zooming away at speeds of around 1,000 kilometers per second. To put this into perspective, at 1,000 kilometers per second, you could travel around the entire planet in just over 40 seconds, about 3,000 times faster than the speed of sound in the air. But how do these stars attain such high velocities? There are several possibilities, but one main scenario involves an interaction with a galaxy's supermassive black hole. To understand this, imagine a binary star system, where two stars are bound by gravity and orbit each other in harmony. Now, picture this stellar pair wandering too close to the supermassive black hole at the galaxy's center. The intense gravity of the black hole disrupts the binary system, capturing one star while slingshotting the other away at incredible speeds, fast enough to leave the galaxy. This ejected star becomes a hypervelocity star. Some alternative theories suggest that a star can also be expelled from a binary system when its companion star undergoes a supernova or due to interactions between galaxies. Although the existence of hypervelocity stars was first proposed by astronomers in the late 20th century, the first one was discovered in 2005. It's estimated that a star is ejected from the galactic center every 100,000 years on average, and astronomers believe around 1,000 hypervelocity stars are racing across our galaxy. But what's really fascinating is that some of them could be from the Andromeda galaxy. However, with approximately 400 billion stars in the Milky Way, locating these hypervelocity stars is significantly more challenging than finding a needle in a haystack. Locating stars that have traveled to the Milky Way from neighboring galaxies is even more difficult. So, astronomers first ran simulations. They began by examining the movement of the Milky Way and Andromeda galaxies relative to each other. Then, they created a model that accounted for the gravitational forces in the system, considering both visible matter and dark matter in the galaxies. With these conditions in place, the team ran simulations to track the paths of hypervelocity stars. They modeled the trajectories of 18 million hypervelocity stars under two scenarios, one where the Milky Way and Andromeda have equal masses, and another where the Milky Way is about half the mass of Andromeda. They started the stars at random positions around the center of Andromeda and gave them random directions to ensure the simulations were realistic and covered a wide range of possibilities. Next, the team analyzed the speeds of the hypervelocity stars as they traveled toward the Milky Way, using both mass scenarios. They discovered that a small percentage of these hypervelocity stars could actually reach the area around the Milky Way. While many hypervelocity stars maintained their initial velocities throughout their journey, some slowed down enough to be captured by the Milky Way's gravity. When looking at a sky map showing where these hypervelocity stars are currently located as they approach the Milky Way, we see their positions around the center of the Milky Way in two different scenarios based on mass. In both cases, the stars are spread out almost evenly. However, there are a few more hypervelocity stars in the scenario where the Milky Way has equal mass to the galaxy they come from. This is because, with equal mass, the gravitational pull between the two galaxies is stronger, allowing the Milky Way to capture more hypervelocity stars compared to when the Milky Way has only half the mass. The research team also compared the positions of these simulated stars with actual data from the Gaia mission, which maps the positions and trajectories of stars in our galaxy. The comparison showed a good match, supporting the idea that hypervelocity stars from Andromeda have indeed migrated to the Milky Way. The study concluded that, depending on the model assumptions regarding the galaxy's masses, the number of hypervelocity stars from Andromeda present in the Milky Way at any given time could range from 12 to 3,910. Even though this is a small number, the study suggests that the migration of hypervelocity stars between galaxies is real and measurable. This hints that the Milky Way and Andromeda have already begun their star exchange program. The second evidence comes from the halos of the two galaxies. A galactic halo is a nearly spherical region surrounding a galaxy, encompassing both visible and invisible components. Andromeda's halo is a large web of gases that extends out and around its spiral of stars. Its gaseous halo is invisible to the naked eye, but if viewers on Earth could see it, the halo would appear about 3 times the width of the Big Dipper. Mapping the halo of the Andromeda galaxy is quite challenging, so astronomers devised a brilliant technique. They examined the light from 43 quasars positioned behind the Andromeda galaxy. Quasars are extremely bright centers of distant galaxies powered by black holes. These 43 quasars are spread out behind Andromeda's halo, allowing researchers to study different regions of it. By observing how the light from these quasars is absorbed by Andromeda's halo, the team could see how this absorption varies across different areas. Using data from the Hubble Space Telescope, researchers found that Andromeda's halo extends 1.3 million light-years in our direction and 2 million light-years in other directions. This is a larger area than previously reported. Since Andromeda is about 2.7 million light-years away from us, its halo reaches nearly halfway to the Milky Way. This means the halos of the two galaxies are already bumping into each other, and the epic collision has begun. The timeline of the Andromeda-Milky Way collision is a fascinating sequence of events, and here's how it will unfold. Andromeda won't collide with the Milky Way head-on. In about 3.75 billion years, the galaxies will prepare for their initial collision. As the galaxies pass through each other for the first time, the gravitational forces will be strong enough to disrupt their structures significantly. This will trigger a burst of star formation, and this is what our skies may look like. This first passage will not result in an immediate merger but will fling the galaxies apart after their initial encounter. After the initial passage, the galaxies will